Hey scholars, welcome to Math Savvy. This is Stephanie, and today is an exciting day because we are starting a new series on real analysis. And before we get deep and dirty and into the subject, I'm going to emphasize that this class is very proof-based. And so this video is going to cover how to solve a proof, an introduction to proofs, and kind of some extra help with some higher level proof-based math classes. So without further chit chat, let's begin. Let's talk about what a proof is. A proof is an argument, pretty much deduced from statements that we assume or know to be true. The goal is to deduce these statements in order to get to the statement we're trying to prove. Okay, pause girly, let me clarify that really quick. So we're starting with the statement that we're given, and we use information based on the statement to try and get to the statement that we're trying to prove. This information that we get from this side to this side can be logic, it could be definitions given in class, it could be just simply rearranging the previous statement. A tip is that this given side isn't always going to be obvious, but the prove statement is always followed by prove that or show that. And you always want to write these things down first. It is an argument, so the more you detail out every single step, the more credible your argument or proof looks. And a tip is that sometimes you want to work backwards to really get somewhere. All right, back to the example. So let's look at an example. Prove that for all real numbers, a and b, we have ab is less than or equal to a squared plus b squared over 2. So for most people, when you're starting proofs, you're like, okay, how could anybody ever get this? It doesn't make any sense. How can we get from the statement on the left to the statement on the right? So first step to any proof is to write down what you know. Let a be in R. Then let's do some little scratch work to kind of get an idea about what this problem is about. So we have ab is less than a squared plus b squared over 2. Let's move the 2 over, and then we can move the 2ab over to the other side. And we notice that that is a factorable expression. So let's write it down. A minus b squared. Perfect. So that is always going to be greater than 0. As we can see, that is just a property of square numbers. They're always going to be positive. Anyway, so this is always true. So we kind of got somewhere, right? So now let's make this formal. Okay, let a and b be in R. A minus b must be in R because that is just a property of real numbers. Great. So then a minus b squared is in R, property of real numbers. So we know we use logic to say that a minus b squared is in the real numbers. And we know that a minus b squared is greater than 0. So let's rearrange, do exactly what we did before, but do it backwards. And then we get to the statement that we're trying to prove. And la-di-da, there we are. So this is a formal proof. That is completely acceptable. That is a 100% formal proof. So we found this by working backwards, really, but we want to make sure that the right-hand side work was purely just scratch work. The left-hand side that we worked out, we started with the given statement, got to the proof statement, and that is a formal proof. So one of the best ways to really get started on practicing proofs is to know the different methods that mathematicians use to solve these proofs. Great, so now we're going to talk about proof by contradiction. This is the first type of proof that is very common. It's a very common method that uses the negative of the statement that you're trying to prove to get to a contradiction. Prove x equals 5 is the only unique solution to 5x plus 7 equals 32. Usually when you're trying to prove uniqueness, you will definitely use proof by contradiction. So we're going to assume that y not equal to 5 is also a solution. This is the contradictive statement. So then we work out 5y plus 7 equals 32. We solve it out. using algebra, and we get that y equals to 5. So that is a contradiction. We see that little arrow, that lightning look arrow, and that is a common symbol that people use for signifying that this is a contradiction. So therefore, we prove that x equals 5 is the only unique solution to 5x plus 7 equals to 32. Great, so that is proof by contradiction. Next, we will look at proof by induction. Okay, wait, what is induction really quick? We want to start out with the base case for natural numbers. It's n equals 1, but we're just going to use an arbitrary k, prove that statement, and then given that that's true, we want to try and prove the k plus 1 case. If we prove that both of these are true, then we pretty much proved all of the natural numbers, and it's as simple as that. So let's look at an example. Prove by induction that for all natural numbers n, 2 to the n is greater than or equal to n plus 1. So for all proof by induction cases, we're going to start out with a base case. For natural numbers, it's going to be n equals 1 always. So we start with n equals 1. We just plug it in at this point. 2 to the first power, which is 2, is greater than or equal to 1 plus 1 equals 2. 2 equals 2. Therefore, the statement is true for n equals 1. Easy? Good. Second step that we do for all natural numbers, n is greater than 1. So suppose we have a natural number k, 2 to the k is greater than or equal to k plus 1. Then we have 2 to the k plus 1. We plug in the k plus 1 case, which is equal to 2 to the k times 2, which is greater than or equal to 2 times k plus 1, which is 2k plus 2. It's always going to be greater than k plus 2, which we can rearrange as k plus 1 in parentheses plus 1. Great. So in sum, we have 2 to the k plus 1 is greater than or equal to k plus 1 plus 1. We prove this statement by first showing the base case and then moving on from there. That is, in essence, what induction is. And that's our last proof example. Don't forget to check out our tutoring services at math-savvy.com. Like and subscribe, and leave a comment below what you want us to cover in our real analysis series. I am happy to help. Thank you so much. Have a good one.